Forgot I need to press recording. Sorry. Okay. Yeah, so quick agenda about the presentation, application principles and challenges in multimodal AI. So first, let's go over some of the multimodal application that we've seen both historically and in the modern day and age. So one of the earliest examples of multimodal research is in the field of audio visual speech recognition. And some of these early models in this domain is based on hidden macro models, which is a probabilistic graphical model. And they were pretty popular in the speech community back then. And even though audiovisual as speech recognition research is no longer common these days, it's actually seen really interest in the past few years with things like voice generation and speech synthesis, for example. Multimedia content analysis is another important category of multimodal application. Some of the earlier approach for indexing and searching multimedia videos was based on keywords. And obviously there's a couple of problems associated with like searching only based on keyword. And therefore, there's a lot of recent research that has been focused in state-of-the-art work to improve multimedia content analysis, like automatic shot detection and movie summarization. And this diagram I put here on the slide was like from a paper that focused on movie summarization. Then the third category of application was established in the early 2000s around the emerging field of multimodal interaction. And this field want to achieve the goals of understanding human multimodal behavior during social interaction. These two links I put here on the slide are two famous datasets, landmark datasets of video recordings that the researchers used to understanding, interpersonal dynamics between speakers and listeners. And then finally, another category of multimodal application emerged back then was on media description. And specifically, we can look at image captioning and visual question answering. So image captioning is in the type of task where you want to generate a text description based on an input image. And visual question answering is another task that want to address some of the evaluation challenges based on image captioning, and the goal here is to answer a question about an image, right? So look at the modern day and age, we can see multimodal AI being used to tackle a wide range of applications across various industries. So one very exciting application is in the field of autonomous vehicles. And in AV, right, multimodal AI can help improve safety and navigation by integrating multiple sensor modalities such as cameras, lidars, and radar. So this image here is actually from a startup called Wave, and they did a lot of work in building foundation models for self-driving car. And this is pretty exciting work that I discovered when they train a model on the self-driving vehicle and basically so like build a proprietary data set with a lot of footage, which is super cool. And then another area where multimodal AI is making advancement is in healthcare. Here, it can assist with the diagnosis and treatment of disease by analyzing medical images, text data, and patient records. So combining different modalities can provide a more comprehensive and accurate assessment of patient health. So this picture is from a survey paper on Nature that look at different foundation models for generalist medical AI. So highly recommend checking it out if you're interested in healthcare and state of that in this field. Furthermore, multimodal AI is also used in the entertainment industry to create more immersive and interactive user experience. So for example, VR and AR rely heavily on multimodal AI to create seamless interactions between users and their digital environment. Additionally, it's being used to generate more engaging and personalized content, such as custom recommendation and video generation, right? So this is an image from a model from NVIDIA called Latent VM, where they did a lot of work on generating videos from scratch. And there's a lot of other companies in this space as well. So my assumption is that as folks become more interested in generative AI, they will keep exploring the potential of multimodal AI. And we're probably going to see even more creative and impactful application being emerged. So that is the first section of the talk. And for the next part, I want to go deeper into the theoretical foundation of the field and look at the field from an academic perspective, right? So I discovered a survey paper by Carnegie Mellon earlier this year, and in that paper they present the three key principles of modality in multimodal AI, including heterogeneity, connections, and interaction. And for the next 3 slides, I will kind of skim through the definition and explain their significance. So the first one is heterogeneity, and this means that different modalities, they are heterogeneous, meaning that they often exhibit diverse qualities, structure, and representation. So, for example, right, like an image and a speech recording of the same event may convey different information, and therefore each of them require unique processing and unique analysis. And in the survey paper, the author presents the 6 dimensions of heterogeneity: elements, distribution, structure, information, noise, and relevance. So these measure the differences in terms of like the frequency and likelihood of these elements, the underlying structure, distribution of noise, the relevance to the specific task, and the information that that is compressed in those input data. The second principle is connection, and the idea here is that these modalities often share complementary information and can be combined together, right, to generate new insights. And so from a theoretical perspective, as a researcher, you can study this connection either through statistical analysis of the association or via the semantic correspondence. So the bottom-up reasoning approach for statistical side involves statistical association and statistical dependence. So statistical associations mean that the values from one variable relate to another's value, and statistical dependence mean that you need to understand the exact type of dependency between 2 elements, right? So looking at from a statistical perspective, this is very important for us to modeling joint distribution across modalities, right? So let's say if you want to match a text sequence with an image, you need to be able to find, there's the association independence in the embedding space, for instance. And the top-down reasoning approach is on the semantic side here. So it involves semantic correspondence and semantics relations. So semantic correspondence means that you want to identify, which element in one modalities have the same meaning as another element in the other modalities, right? And then semantic relations include an attribute that describes the nature of the relationship between 2 modalities elements. They can be logical, causal, or functional. So identifying semantically related connections is very important for some of the higher order reasoning tasks. And I will go over the importance of multimodal reasoning in a couple of slides later in the presentation. Then finally, different modalities often interact in different ways when they are being integrated into a task. And this interaction can take many different forms, right? Such as if you think about how an image or a speech recording can be combined together to help recognize an object or a person. So understanding this interaction is very crucial for building effective multimodal AI models. And in the survey paper, the author proposed 3 dimensions of interaction. The first one is interaction information, and this investigates the type of connected information involved in an interaction. Secondly, interaction mechanics are some of the functional operators involved when integrating different modalities for the task itself. And finally, you have interaction response, and this study how the infer response can dynamically change in the presence of other modalities. So let's say like when you try to build an application that's highly visual, then the image modalities might be like heavily dominant, right, in terms of it representation compared to say like the text, right? So that's an example of a response. So building on these 3 core principles that I just mentioned in the survey, the author provide 6 different research challenges associated with multimodal research. And each of these research challenge grapple with answer like a specific question. So representation, it answers the question of like, how can we learn representation that reflect the diversity and interconnection between different modalities? Alignment, try to answer the question of like, how can we identify cross-modal connections and interaction between modalities? Reasoning is like, how can we compose the knowledge that help exploit the problem structure for a specific task? Generation, how can we learn a generative process to produce the raw modalities that reflect cross-modal interaction, structure, and coherence? Transference, how can we transfer knowledge between modalities? And finally, we have quantification. How can we conduct empirical and theoretical studies of multimodal learning? So those are the 6, core research challenges, and I definitely highly recommend you taking a look at the paper. Yeah, so this is the. Take a look at the paper if you got a chance. It doesn't load right now, but I can share it in the message afterwards to kind of go if you're interested in the theoretical definition of the field. But for the sake of this presentation, I want to focus on the 3 challenges that are highly relevant to industry application, which is representation, reasoning, and generation. So let's go over each of them one by one. So multimodal representation. So how can we like learn this different concept, right? And how they react to each other. Just give an example, right? So let's say the idea of a beautiful picture is very grounded in the visual representation. And so it's really hard for human to describe the concept of beautiful picture through natural language or other non-visual way. And therefore, it's important if we can learn the joint embeddings that use different modalities to represent such concept. And so the primary goal of multimodal representation learning is to narrow the distribution gap in the joint semantic subspace while maintaining the semantics of each of these modalities. And some of the recent research has focused a lot on multimodal pre-training. And this means that you want to create like a pre-trained large model that can, that already has been pre-trained on a combination of different modalities. And so therefore it can make a lot of inference towards downstream tasks. And so actually write a whole essay and give a talk about this topic back then. So I recommend you check it out. If you have the time to take a look. It's about like how foundation models are going multimodal. And this model are capable of different multimodal representation learning for a variety of like downstream tasks. So I list a couple of like examples here in the slide. Image plus text plus speech. You have video with text, video with audio and text, right? So you can take a look at some. Here are just like some sample examples of model that has been pre-trained on the combination of these semantic. And obviously there's a lot more as the field evolves, right? So I want to highlight 2 unique example that is very like powerful in terms of the semantic representation. This one is called Gato by the team DeepMind, and this is a generalist agent that can perform more than 600 tasks, include things like conversation, photo captioning, outperforming humans in archery games, following instruction. And the guiding principle for Gato is to pre-train the model on a wide range of tasks, right, including diverse modalities like image, text, button presses, right, and a variety of the discrete and continuous observation and action. So this is like the link to the paper if you're interested in checking it out. It was written back in May 2022, so just about a year ago. Highly recommend it. Check it out. Image by is another one. So this one pretty popular. A lot of our speakers in the past session actually mentioned image by. as a type of like frontier model. So it combines 6 different modalities: text, image plus video, audio, 3D, thermodynamics, and IMU, initial measurement units. And although it's only a research project released by Facebook, it points to a future multimodal AI system that can create immersive multisensory experiences. Right? So this is the link to the paper if you want to check it out. So the multimodal pretrained model have a lot of cool application, but obviously there will be limitation, right? And this is a jump back slide that I want to go cover the key limitation of pre-training, right? So the first one is around scaling laws bottlenecks. So if you are deep into the LLMs and Gen AI space, you're probably familiar with the concept of scaling laws. It comes from a paper by OpenAI back in 2021. And the core assumption is like, if you scale up the number of parameters and the training data, then the performance will go, exponentially, based on the scaling dimension. And this applies to multimodal setting as well, right? But obviously, there's bottlenecks in terms of compute resources and instability in the pre-training process, right? Especially when you extend pre-training to multimodal setting. And some of the papers that study scaling laws will become increasingly important for the years to come. So this experimental setting here come up with a paper that look at how scaling laws can be applied for generative mixed model language model, which pretty relevant for this limitation. The second limitation is around knowledge transfer. Knowledge transfer is the concept of like fine-tuning a model to a downstream task. And matter of fact, when you fine-tune a pre-trained model on another task, it actually might have a negative consequences to the robustness and performance of the model. So this diagram here come from a paper that basically look at how the author try to fine-tune the clip model from OpenAI on the image data set, and they learned that fine-tuning clip actually reduce the model's robustness to distribution shifts, and not fine-tuning clip and just simply apply it directly to the downstream task can actually get your better performance. So this type of finding suggests that fine-tuning, knowledge transferring is still a challenging task that worthy of future research investment, right? Then we have architecture restriction. So generally, most of the pre-trained multimodal models that I'm aware of use the famous transformer as the model backbone architecture. However, a transformer might not be suitable for some modalities, right? It is very likely that sometimes you have to design like a specific architecture in certain contexts, and therefore formalizing when and where these contexts occur is a very important future research direction. Domain-specific and high-stake problems. So some of the pre-trained model, although they perform super well on a wide array of tasks, their performance might go down when being adapted to some of the downstream tasks that require highly specific domain knowledge. For example, in discipline like healthcare and legal, they will have very low error tolerance for some of the models being deployed in real-world setting. And therefore, in such scenarios, relying solely on the system view from pre-trained model will, pose a lot of risks associated with them, because this model currently are black box, and there's no way to control their real-time behavior in a predictable way. Compute requirements. So this one kind of relevant and synonymous with the scaling law bottleneck. So some of the large pre-trained model have a lot of compute restriction due to the size and complexity, and therefore training and inferencing this model is very expensive, right? And so therefore we need to think about ways to build more efficient architecture, optimization techniques like distillation, pruning, and quantization in order to reduce the cost associated with this large model. And finally, robustness. So despite the impressive performance on a lot of tasks, some of these large multimodal models can be vulnerable to adversarial attack. And this vulnerability has very important application, especially when this modeling be deployed in high-stakes application. So yeah, I hope the coverage of these 6 limitations poses the picture of like the complexity of real-world deployment and how like just simply taking a research project into the real world is not a simple task, right? So I want to quickly go over the this concept called cross-modal interaction. So one of the goals of multimodal pretraining is to capture the connections and interaction between different types of data, right? And the simplest way to do this is through transformer. So Michael, I saw your question about transformer for sequence structure. Yeah, because like the attention mechanism allow you to pay attention to the most important part of the input data, right? And then you sequentially like process the data, and therefore that's why it's like very powerful for language like protein generation and video, for instance. Yeah, and that's why a lot of work in this domain that have this temporal dimension still rely on transformer, as the backbone architecture. So yeah, going back to this slide, right? The goal of like pre-trained multimodal model here is to learn how different modalities can align with each other during the pre-training process. So there's a couple of ways that you can do this. The first one is you can build like a frozen model and as the backbone, and you like add a bit of like a different operation on top of it. So this paper, this work is called Fromage, and Poisson retrieval over multimodal data for auto-regressive generation, and it build like a underlying frozen model that allows you to take advantage of that frozen model and then do a lot of operations on top of that. The second way is to align sequences up to modalities. So, so for example, right, given some text input, you can train a model to predict which audio tokens come next, right? So this could help align sequence of text with audio. And you can think about the same thing with like text between text and visual, text with audio, visual with audio, right? And finally, in a couple of multimodal model that I come across, they design like a sub-module sub-network specifically in the architecture to represent individual modalities. So this is an image from a paper called Parameter Efficient Multimodal Transformer for Video Representation Learning. When you can see here, they have a visual layer, an audio layer, right? And then a multimodal transformer layer, and each of them capture that respective modality. And so this area of research could be explored further to understanding cross-modal connections better. Yeah. So what is the future direction of pre-trained multimodal model? So given the surge of large language model, it is very possible that natural language could be the best modalities to guide multimodal pre-training. It is found that these large language model are strong learners in various downstream task domain, and therefore you can use them as like the learning as a learning objective, right? In fact, one of the speakers from our webinars a few weeks ago, present like a whole slide where talk about like large multimodal model, and just use like LLMs as a guide to help you discover how this multimodal model gonna unfold, right? So two things I want to point out why language is such a good guiding modalities, right, for this process. Number one is that language is naturally sequential, and therefore it is very useful to integrate other modalities into language, basically. So an example of that is the family of Socratic model. And this group of model use language to guide the composition of foundation models for multimodal tasks. And they also use language to align and fuse information across these different modalities, right? So they literally just prompt different subtasks using an LLMs. So yeah, that's why it's called prompt engineering for multimodal application. And secondly, language is what us humans use to describe objects and communicate, right? So using text as a decoder for large pretrained model can help humans interpret and dissect what the model is learning during the multimodal pretraining process. And given the popularities of OpenAI ChatGPT, I came across a couple of work that basically use ChatGPT as the backbone, such as Visual ChatGPT and Multimodal GPT, that can conduct multi-dialogue with humans. So this is an image from Multimodal GPT, a repo where you can, conduct dialogues with the model itself. Yeah, so that's the end of the session on multimodal pretraining. And obviously that is like the main focus of the research committee thus far, which is how you like represent, right, these different modalities in the same data space efficiently, right, and effectively. So the second challenge we want to cover is multimodal reasoning. So reasoning is defined as composing knowledge, usually through multiple inferential steps. And the goal here is you want to exploit the problem structure for a specific task. So how can we like understand this concept of reasoning, right? One way to do so is to follow a logical chain to reach a conclusion. And this is called chain of thought reasoning. The idea is like you want to basically like have like step-by-step explanation of how the model make the decision, right? And this is an example, like asking the model to keep the rationale and asking the model to keep the rationale before giving the answer, right? And this is from Amazon, a work called Multimodal Chain of Thought. Another approach is to create a formal taxonomy for reasoning. And with this taxonomy, you can understand and reason with the available information. And the taxonomy can be classified along different dimensions. And I'll list out here a couple of dimensions that you can, design the taxonomy for. Right? And ideally, this taxonomy should contribute to different subgenres of reasoning, and namely like ensuring consistent reasoning and sufficient evidence. So how do pre-trained models reason? So some of the large-scale pre-trained models are very powerful at learning representation without explicitly modeling reasoning. Therefore, like it's very hard for researchers to make them interpretable, right? Compared to some of the traditional neural networks approach just a few years ago that have like a symbolic reasoning component with it. So I list out here a couple of methods that I discovered for how like discovering the reasoning abilities of multimodal models. So latent space visualization. So this one means that you want to visualize the joint embedding space between, say, language and vision, right? And this is a method well popularized by the CLIP model by OpenAI. Second method is to inspect the attention score in each of the head of the model. And so for example, this is the work from Visual Bird where they did an analysis and they plot out where in an image the model pay attention to, and they can quantitatively measure the weights that each of the head capture, right? So this is the link to the paper you're interested in, link to the report you're interested in, like dive a bit deeper on. Stress testing. So this one means that you can change the input to a model to see how that affects the output. You can like remove a certain input, right? And or maybe you can add like fake inputs to the model and see how the performance of the model change. So just make sure that you want to, just like how you stress test software before you release into production, like you want to stress test your model and see how it performs in diverse settings with diverse distribution shapes, right? Persistent system degradation. This one means that you want to intentionally give the model less information to see if it can still reason well or not. And finally, reasoning parts. So this one's similar to the chain of thought image that I give in the last slide. The idea is you want to like, it's like a decision tree, right? Where you want to come up with different branch and draw out like different branch that the model going to reason, right? So this image come from a paper called recursive grading tree, where they like basically design like a tree-like structure to understand the reasoning process. Yeah, so those are different methods to uncover reasoning abilities of pre-trained model. And these are some of the key challenge in multimodal reasoning. The first one is like designing the architecture and designing the training setting, right? Because no one right now knows the best architecture for multimodal learning yet, and therefore it's very hard. It's still an exploration for a lot of the community to discover the best way to, to design the model and train the model. I personally think that reinforcement learning is one of the training paradigm that we should consider, because in reinforcement learning, there's an exploration phase where the model learns to come to a solution without explicit supervision, right? And therefore, it can allow for a more natural and guaranteed step of reasoning than with supervision. Yeah, Gary, I will make the slide and the recording available afterwards. The second challenge with multimodal reasoning is evaluation, right? Because it is pretty difficult to, when you work with like different modalities, like it's really hard to dissect and know which modalities are necessary for the reasoning process. And so it's not clear like how you can evaluate that process. So I input here in the slide a work called MMVET, and this is from a webinar talk from Lindsay Lee, one of our speakers, just a few weeks ago, where she introduced this promising evolution benchmark. And this benchmark, they focus on the integration of different core vision language abilities, such as recognition, OCR, knowledge, language generation, spatial awareness, and mathematics. And it's like it was the first step to like help evaluate, right, these multimodal models. So looks promising in my opinion. And finally, there's a challenge of creating multimodal reasoning data set, right? How can we come up with relevant data set that allow us to untangle the reasoning part of the model, right? So that's still also a challenge. So like with all these challenges, right, you might wonder, why do we even need reasoning, right? Why can't we just like get the results right away and without thinking about the process it got to that output. So there's two things I want to provide to answer this question. The first one is that right now, like when you search for some information, that process relies on just entering queries into a particular format, right? To get the answer and the rationale. But since the introduction of ChatGPT-like products, right, it's a different type of interface where you chat and have a conversation with the product itself, and therefore you can come up with like very specific problems, unique question to ask the chatbot and get an answer with an explanation. And so that related to the first part, which is getting curated logical rationale in reasoning question, is very crucial because we want to verify that it doesn't hallucinate, right? So in the context of multimodal model, it's important if we can get like a rationale that go beyond text. So this is an example from a work called GradCam, which provide like a visual rationale of the model, right? So it actually like demonstrate like a visual heat map of where the model looks. And the second reason is that retrieving evidence in reasoning is important to verify the reasoning models, right? And knowledge graph is another domain in the database community that I think can be relevant for this process. So the idea is that you can use a Pretrained model to generate the answer, and then you query a multimodal knowledge graph to provide evidence, similar to how like us human use Google for confirmation of the sources, right? And there's a lot of like newer search engine in the past few months, well, in the last year or so that do this. You know, Bing chart is one example, UChat, and the example here is from Perplexity, and they all like have these sources and citation, right, to verify the truth, they give the citation to make sure that that you can follow through and check the source, right? So yeah, Perplexity, this is linked to it. So if you can do something like that, similar to that for multimodal knowledge graph, I think that could be a great next innovation, right, for anyone who want to build products, build multimodal application. Okay, and then finally, this is the last part of the presentation. We'll look into multimodal generation, and this one involves learning a generative process to produce raw modalities that reflect cross-modal interaction, structure, and coherence. And obviously, like this particular domain has been very popular recently, given the rise of generative AI, right? Thanks to products like Midjourney and ChatGPT light of the world. So within the domain of generation, there's actually 3 subtasks that I want to cover. So the first one is summarization. This task is about making a short version of some information that only includes the most important parts. For example, if there is a news video, the short version would summarize what was said in the video, and then the summary can also include some pictures from the video. There are two main ways to making the summaries. The first bullet point is extractive approach, and this means that you want to remove words or phrase from the original information to create a summary. So, for instance, video summarization is a type of extractive summary that can encapsulate the most important part of a video. This is an image from a survey on video summarization using deep neural networks that I discovered. And then we have abstractive approach, and you want to use a giant model to create a summary at different levels of granularity, right? So here's like maybe you want to only get the summary from a text standpoint, right? So you want to get a quick text summary from a video, for instance, right? But also maybe you want to get like a text plus image summary of a video. Then you can like make it more granular, and like associate the image with the text in your output summary, right? So that's a nuanced difference between extractive and abstractive. And you have translation. So translations involve translating between 2 different modalities while keeping the semantic connection and information content the same. And here, some of the recent approach in translation can be divided into 2 groups. So example-based mean that you use some chain examples to translate between modalities, but guarantee the fidelities of the data. And then generate models. So this one simply means that you can translate 2 new examples from scratch, like no training set, like it's a few short generation. Obviously, like most of the work in the generative models has been like quite popular recently, but like obviously there's a lot of challenge with the quality, the diversity, evaluation, etc. This is an example of a work called Frozen that more follow the second item. I just want to put here in the slide. Yeah, so this is translation. And finally, you have creation. So creation, yeah, like means that you want to create things from scratch, right? So this involves creating novel high-dimensional data that included text, image, audio, video, and other modalities as well. And this can be done using small initial examples. However, like it is quite difficult to do this process because the creation process needs to be conditional, means that you want to be able to preserve semantically meaningful mappings from the initial seed modalities to future parallels modalities. This creation process also need to be synchronized. Synchronized means that you want to keep, you want to be semantically coherent across modalities, right? So not like when a speaker says something, you wanna keep it like associated with the visual of the person, right? Not like with some other speaker, right? Stochastic means that you want to be able to capture as many possible feature generation given a particular state, and then auto-regressive across long range. So this one means that you want to be able to generate far in the future while maintaining long-term memory, right? So many modalities have been considered as target for creation based on GPT model. Language generation is obviously one of the most popular one. We also see some of the work in speech and sound generation. So this example here is from DeepMind speech synthesis with WaveNet. So they generate like speech and sound from scratch. You also have work in image generation, right? With latent diffusion, you can generate computer graphics, talking heads, and like I think for video itself, video generation is a new field that has come across recently, and obviously you've seen. I mean, if you are familiar with like say Runway Gen 2, this is an example of them make a video. This is from Facebook. So these are some of the work that attempt to generate video from scratch using text. Very exciting, but like there's still a lot of challenge with like complete generation of realistic videos, text and audio, right? So here's some of the challenges in multimodal generation that I want to go cover. So there's 4 of them. Number 1 is controllability. So this is important because as a user, you may want to create let's say they do text to image generation, right? Then you want to do it in a very specific style, right? So to achieve that level of controllability, then you need to be able to configure the model itself, maybe through latent diffusion model. This is from the famous stable diffusion model, right? Maybe you have to use different sampling scheme, right? So there's a lot of like trick and tips that you need to work on, to achieve that level of controllability. The second challenge is compositionality. So this one means that you want to be able to understand complex inputs and generate appropriate outputs across different settings, right? And this is like still a big challenge because like even in the large language model and language and vision model, it's still very hard to interpret like say language from a different not that is like from a low resource language, right? Like not English, like Hindu or African language, right? So like it's even a more bigger challenge when you think about like extending to different modalities. So synchronization here is very critical to synchronize modalities appropriately for the generation to be semantically coherent. So for example, right, generating dialogue in a video involves synchronizing a unique voice with the person speaking in the clip, and then the voice also need to remain consistent across different sounds, different utterance. So evaluating this synchronization is quite a big challenge, right? I input here in the slide this clip from SyncLab, which is a startup that work on real-time lip syncing. They do video to lip synchronization, and the co-founder of SyncLab, Pradeep, he was giving a talk at our webinar a few weeks ago, and yeah, it was pretty exciting, right, to see this type of work being developed, right? Then finally, there's a chance of capturing long-tail phenomenon. So how can we capture long-tail examples that may not be well represented in the training dataset? And this is related to the mode collapse problem if you work in like GAN's model back in the days, right? And so, obviously a lot of challenge here. Sometimes when you text as a prompt to generate things, the language description can be vague or very specific, and therefore like maybe we need to like use different type of representation to prompt the model, right? So like image to video or video to video, for instance, instead of just using language. Yeah, so these are the 4 major challenges. I want to reserve one slide for ethical issue because I think this is something that we probably do not think a lot about as practitioners, as technical people, but I think, generation obviously have a lot of real-world ethical issue that at least we should like pay attention to. So number one is job displacement, right? So an early work by OpenAI look at how like this model are getting better at doing things that used to be done by people. And therefore, like we should find a balance between letting machines do some tasks and having people to do the other. Plagiarisms and privacy. So yeah, like copyright issues, training data, right? How can we make sure that this model doesn't just steal the content and produce things without attributing the existing sources, right? So this image comes from a work called GAN fingerprints. This is an attribution model that help identify the source used by generative models and provide digital signatures for the authors in order to safeguard the intellectual property. So this type of work, I think, could be somewhat relevant for the future of multimodal generation. Human creativity. So, how can we build models that are not just replace human creativity, but like assist and improve it? And finally, defects, cyberbullying, and fake news. So there was like a big deal like a few years ago, like defects, right? Like fake content, and I think still is like this day, especially with hallucination and things like that. So yeah, how can we prevent this model from generating such type of fake content during pre-training? Was I think like as a research committee, we probably have to think about. Yeah, so this is a quick slide on the conclusion of the talk. I go over the historical and modern application of multimodal AI, some principles, and the key challenges, right? And I think like, some of the recent advances in foundation models has shown a lot of exciting work. And actually there's a lot of company that has been spun out to like, work on this space. So these are just a few that I came across. So you like Ideogram, for instance, a competitor with Midjourney and DALL-E 2. There's Contextual.ai, a startup that building, I think like vision augmented language model. The co-founder was come from Facebook, so I think they have a lot of like research background in that domain. And this is a new multimodal assistant from Breakout.ai. And according to like the blog post, this enterprise grade ready, and they can process like different type of modalities, supporting like different languages and retrieval augmented generation, right? So super exciting. And yeah, like since we hosting hackathon tomorrow, like with 11 labs, so like all this company in this space is also like very excited to help support the work of the field. Yeah. So I want to reserve like one quick slide for 12 labs because I want to emphasize kind of our commitment to build foundation models for multimodal video understanding. And our goal here is to build the kind of video model that can combine and you understand the world as we human do. So if you're not familiar with 12 labs and the product that we do, I want to quickly show you this demo of our product and some of the new capabilities in both like embeddings and generation. So this is a video from our product manager who's going to quickly walk through how it works. This is an example of video to text generation, as you can see. Oh no, so okay. I can share the screen and the chart afterwards. This is a video chatbot capabilities where the model answer the question, give an answer based on the question from the prompt. So it really display the multimodal reasoning capabilities that I mentioned in my slide a while back. Yeah, so you ask question like what's sputtering and being promoted in video, right?
On her journal, and it was hilarious.
So I turned it into a template so that you can do the same because I'm obsessed with this LLM model. It's amazing. It's my best friend. So here's the Jupyter notebook, and you can find it on our GitHub repo. And yeah, basically I show you like where to upload your data and how to fine tune the model and etc. And it's really easy and fun. And by the end.
Yeah, so that was a quick demo of the product. And let's go back to my slide. Yeah, so that's the end of my slide. Actually, I wrote a blog post on this topic on a blog. So you want to take a look and go over some of the relevant references that I present in the talk today. Feel free to check it out. Yeah, and I'll be sure to send it. Actually, I can send a slide right here. Yeah, just go to this one. And if you have enjoyed our Discord, feel free to join using this QR code. And yeah, that's the end of my presentation. I realized that like I went over, 4 or 5 minutes. So if you have to leave, yeah, feel free to do so. But yeah, if you have any question, feel free to ask me directly on the call or on the chat. Yeah. Thanks, Fernando. Thanks, Michael, for the question. And I actually put on the demo that I just showed you because for some reason I couldn't share the sound. Yeah, thanks, Serena. Thanks, Marlon. Any work on audio scenes analysis using multimodal? Audio scene analysis? Yeah, so I think like text to speech, right, is like the first thing that came to my mind. Like how do you control like speech, just for example, like the company 11 Labs that we will collaborate with them tomorrow for the hackathon. They did the work of speech synthesis, voice generation, and for that they do like a lot of work in text to speech, right? And so they have to configure the text and speech alignment. So I think I recommend you take a look at that. I haven't come across any work that like use something other than text to produce audio, which makes sense, right? Because audio, let's say audio and image is very different, like visual. Well, maybe I think like anything that work with audio probably going to work with video as well, right? Because video is a combination of like audio plus text plus image. So when you process a video, you already process audio, right? Inherently during that process. So like a lot of the work when we build this model for 12 is to have a dedicated subnetwork which is an audio transformer that capture the audio elements. So like when you do search and when you do generation, that audio component is already being represented and captured through its process. So that's another thing that came in my mind. But yeah, overall, a bunch of other exciting startup working on like text to speech, audio generation, music synthesis. Yeah. So I think I'm excited to see more of those research and startup coming out in the speech recognition community. Yeah. Any other question? If not, then yeah, I can put my name, my email. Gary, my email. Yeah, structure, architecture, but cross training. Yeah, I mean, let me go over cross training. Where is it?
Hello.
David, yeah, go ahead.
Yes, I asked the question. My question is, you can fine tune a model, when you have some kind of data. This fine tune and data transfer mechanisms works only on models training on the same network. I mean, we cannot freeze a network at other layers of different architecture to that frozen network, and that wouldn't be a kind of, for example, transfer learning.
Wait, so your question is like
yes, if it's possible to use another the information learned from, for example, a transformer, to use it in a unit or a convolutional network, for example, or between different architectures, not exactly the same neural network.
yeah, is it yeah, good question. So I personally like haven't, maybe I'm not aware, but like I think like I personally have not seen any work that like do like combine, let's say, convolnet and transformer in the same pre-training paradigm, right? Maybe you can like fine tune it like with the sub, like let's say you build like a video transformer model, right, that can process and understand the video frame, and maybe you want to fine tune that model for a facial recognition use cases. Then during that knowledge transfer facial recognition, you can use a convnet, right, as a sub module for transport learning, right? So that is happening like after pre-training. This happened during the inference. But like in terms of pre-training itself, I personally haven't seen any people that like pre-train transformer and convnet at the same time, right? Yeah, so to answer the question, is it most likely you have to just stick with the same architecture and the same limitation of transformer in this case. Yeah, maybe there's another way in the future where you can, during pre-training, you can actually like and effectively, insert like a other type architecture in that module. Yeah.
Thank you. For example, when Bikugan and Clip came out, Clip, I think, is trained of convolutional networks, the Clip OpenAI model. And these new models, natural language processing, are mainly for transformers. So trying to combine these two models to gain multimodal is actually difficult because they have different neural networks, but they can be used together as agents. For example, I know Clip can be an agent to insert text into a natural language processing model, but this is actually not really multimodality.
Yeah.
So I was expecting something like maybe a convolution network or something that is not a transformer, but is good at images, can be connected to a transformer network that is good at natural language processing to gain this multimodality. I don't know if that's possible. Well, you already say there is no paper yet, but if that will be possible, it will certainly expand the possibilities of multimodality.
Yeah, I totally agree with that. I think that concept is kind of similar to the like mixture of expert idea, right? Where you have like different small expert that is an expert at that specific modalities, right? So you know, ConvNet for vision, back in the day was RecordNet for image or like for speech, right? And I mean, et cetera, and then you just kind of like combine them into generous agent, right? That it's very good at that task, right? Because they use that sub expert, right? But I agree with you, like, you know, like that is like not really multimodal because you don't pre-train everything together. You just literally have like the whole training process for one modalities, and then you only combine the output together, right? So there's already happened after the fact. But yeah, like hopefully in the future we can figure out ways to maybe we can even design like a new architecture different from transformer, right? To do that kind of thing. I think one of my slides about limitation in multimodal pretraining, I was showing like transformer might not be suitable for some modalities, right? I don't know. Like a lot of people are thinking about ways to designing new architecture. So hopefully we'll see some of those in the next few years or so. But still a lot of time from now to then.
Thank you.
Yep. Yeah, Michael.
So just a quick question. Do you think that, I think that, the linear aspect of it, or, the sequential aspect of it is really important, obviously, for these things to work. And so the question is, are there transforms that could possibly convert something to, a sequential, thing that these transformer networks would then work for, would not work for pre-transform data? I'm just kind of wondering, I mean, would there be any difference in training, whether or not the input were transformed or not, or would it be the same? Is it able to find it regardless of the structure of the input? It just seems like it doesn't, so it might depend on transforming the data. I mean, so that it would work with a transformer. Any ideas about that? I mean, like say an FFT, in other words, that the frequencies are shifting in a kind of sequential way. And so versus like the individual sample points, that it may not be able to find it with just, raw audio data very easily, but it could if it, had like a, some type of transform applied to it beforehand. Anyway, I'm just kind of wondering.
Yeah, so your question is like, for sequential data, can we modify the data in such a way that they become appropriate as input for the transformer architecture, right? I think like, I mean, the more like standardized the data is, the better, right? So like for a machine learning model for like an neural networks, OSC is an embedding, right? Like an array of numbers, and those numbers like represent the image, the audio in this case, right? So I think like like as far as I'm aware, like transformer already pretty good at handling sequential data due to the design of the architecture itself, right? And so the more, like I agree with your point, the more sequential the data, the better fit they are for the architecture. So what does it mean to be sequential, right? It means like time series component, for instance, right? Financial data, like the protein molecule, like what is that? The 4 letters molecule. There's a sequential component because like after one molecule, it only can be like another sequence, right? So the model can predict what the next sequence is. If the data is like completely like unpredictable, right? There's no way to predict the next completion of the data, then I think that is really hard for transformer to process. Right. So yeah, I mean,
So it really is related to a measure of entropy of the data that's being used to train it with, right? I mean, ultimately.
Yeah. I mean, yeah, like the less entropy, the better, right? So yeah, I'm trying to think of examples of any data that like have high entropy, but honestly, I don't know. I think like most of the thing in the world like have a lot of structure, right? Like music or sound or like even robotics, right? Like they have sensors that perform an action, right? So there might be other things that like I'm not aware of. Yeah, but yeah. I hope that answers your question. So that's one of the reasons that transformer is so good, because like most of the data in the world is sequential by nature. So yeah, I have to like dig a bit deeper, more research and figure out like what type of data is not suitable. But that may be another question. That's a future question, more research. Yeah.
Yeah, I was just going to say it works so well that I'm tempted to want to force things to be able to use it, if that makes any sense, if possible. If it's possible to force it into that arena that it can learn stuff from it. That'd be great to do because they seem to be so effective.
Yeah, absolutely. Okay, it's 2:48. Well, my time. So we 18 minutes over. Well, thanks all three of you for staying towards the end. I send over the recording when it's become available, and hope you guys enjoy the rest of your weekend. Bye.
Thank you for the presentation.